Welcome back, everyone. In our last video, we saw how our n8n workflow could generate and upload long-form horror videos on autopilot, but some of you on older machines ran into timeouts in the HTTP request node when processing longer clips. Your computer would hang waiting for the backend to finish, and eventually, n8n would throw an error. Today, we're solving that. No more waiting on slow renders. First, head over to the new lesson where we've published updated backend code that addresses a few key issues. Copy that new code and replace it with the existing backend file from your previous setup. Now, if this is your first time working with the backend portion, no worries. You can follow the earlier lesson to set up the environment from scratch. In our case, since we've already created the environment, we'll just activate it. With the environment activated, let's go ahead and install the required packages. Be sure to also install FFmpeg. It's essential for video processing, and the installation process varies slightly depending on your operating system. Once that's done, we're ready to start the server. As usual, the backend server listens on this port. So next we'll use ngrok to expose this port publicly by generating a secure URL. Don't forget to add your ngrok token to your machine if you haven't already. It's a one-time setup. Once everything's up and running, you should have a public URL that points directly to your local server. This is your backend endpoint. Now, let's jump back into our n8n workflow. Locate the HTTP request node that triggers the video rendering and update its URL to the new ngrok link. Before we continue building the workflow, let's take a moment to understand how the new backend code works. The code now includes three main APIs, one to generate the video, another to check the processing status, and a third to download the final video. Just like before, the workflow starts by sending a post request to the generate video endpoint. We pass in all the necessary data, including a callback URL. This callback URL will be triggered once the video has finished processing, and in the future, it could be integrated with other platforms. For now, you can leave it as is. We're not using it in this setup. After posting to the generate endpoint, we receive an immediate success response. This response includes a task ID and a status indicating that processing has started. This is important because it prevents timeouts in the HTTP request node. The task ID acts as a reference label for the video and will be used in the next step to track its processing status. To check the status, we make a GET request to the status checking API and simply append the task ID at the end of the URL. If the video is still being processed, we'll receive a status message saying processing. Once the video is ready, the same endpoint will return a done status. At that point, we can hit the download endpoint, again appending the task ID to retrieve the final video file. This architecture mirrors how production-level platforms handle long-form video processing, allowing us to render even hour-long videos without any timeout issues.
The old clock struck midnight, its chimes echoing through the empty house.
Now, back in our n8n workflow, let's configure the render video node to include the callback URL parameter, aligning it with the new backend structure. To simplify things, I've included the complete and final version of the workflow in this lesson. You can download and use it directly. Here's a quick breakdown of how it's structured. First, we have a function node that initializes and keeps track of the task state. It extracts the task ID from the render node response and sets an initial attempt count to 0. While this node isn't critical for the logic, it helps visualize and debug the flow, acting as a state initializer. As we tested earlier, once the video generation is triggered and we get a task ID, we move to a status checking node. If the return status is done, the workflow continues by calling the download video API using the same task ID. This download step is the same API we previously tested using Postman. From here, the final video is passed to the YouTube upload node to publish the result. Let's also rename the download node to make things clearer. If the status returned from the check is still processing, the false branch is triggered. The workflow waits for 10 seconds, then rechecks the status by calling the same API again. Each cycle also increments an attempt count, which again is just for debugging purposes to track how many times we've pulled the API. You can keep this node or remove it depending on how detailed you want your logs to be. So essentially, we're pulling the status endpoint every 10 seconds until we receive a done response. Alright, let's run the workflow and see everything in action. When the render video HTTP request node is invoked, it immediately returns a message. This message includes a task ID, your unique reference for the video job. Meanwhile, the actual video processing continues in the background. During this time, the check status API will return a processing status. So, we enter a loop that repeatedly checks the video's progress. Each cycle includes a 10-second delay before the next check. This loop continues until the check status API finally returns a done status. At that point, the condition node follows the true branch. From there, the workflow calls the download video request node. This request returns the actual video data file. That video file is passed directly into the YouTube upload node, just like we did earlier. Now, since we've adjusted the node structure, we also need to update the YouTube node parameters. Basically, we'll drag the output values from our YouTube metadata generator, title, description, and tags, into the appropriate fields. That keeps everything dynamically connected and ready to publish. And just like that, we've built a complete production-ready workflow. One that can handle hours-long video rendering without crashing or timing out.